This is literally everything about calculus: where it came from, how it actually works, one slow idea at a time, and where it is quietly running your life right now, and you are allowed to fall asleep. That is not a failure tonight. It is part of the design. The ideas will keep unfolding gently, one after another, like waves arriving on a dark beach, and wherever you drift off, the rest will simply be waiting for you tomorrow night. Mathematics is very good at waiting. So settle in. Let your shoulders sink a little deeper into the bed. Tonight the numbers become words, and the words become pictures. Let's begin. Chapter 1. Imagine you are Archimedes. It is around 250 years before the Common Era. You live in Syracuse, on the island of Sicily, a Greek city of stone harbors and olive groves, close enough to the sea that you can hear it from your workroom. You are already the most famous engineer alive. You have designed systems of pulleys that let a single man move a loaded ship, and a great turning screw that carries water uphill, slow and patient as the tide. Kings send you their problems, and yet none of that is what keeps you awake at night. What keeps you awake is a shape. Take a cone and slice through it at just the right angle, and the edge of the cut traces a smooth, open curve called a parabola. Now cross that curve with one straight line, and you have cut off a piece of it, a shape with one flat side and one side that bends, like a drawn bow resting on its string. The question you cannot put down sounds almost childish. What is the area of that shape exactly? For straight-edged figures, this is easy, and it has been easy for centuries. A rectangle is its base times its height. A triangle is half of that. Any field, any temple floor, any figure with straight sides can be broken into triangles and added up, piece by piece, until the whole is known. But the parabola bends. There is nowhere to lay a ruler along it. Draw a straight-sided figure inside it, and thin slivers of curve are always left over. Draw one around the outside, and you have taken too much. The true area seems to live forever between too small and too large, just out of reach. Your first move is bold and simple. Inside the curved shape, you draw the largest triangle that will fit. Its long side lying along the flat edge, its tip touching the curve at the fullest point of its bulge. In one stroke, you have captured most of the area. What remains are two slim gaps, each bounded by a short straight edge and a small arc of curve, and you notice something quietly wonderful. Each gap is the same kind of shape you started with, only smaller. The problem has not gone away. It has become two smaller copies of itself. So you do it again. Into each gap goes the largest triangle that will fit. Now 4 even thinner gaps remain, and into each of those goes another triangle, and then another round after that, and another. The triangles shrink quickly, and with every round the leftover error, those uncovered slivers hugging the curve, shrinks toward nothing. Then comes the discovery, the thing you prove with slow, careful geometry. Each new round of triangles, taken all together, has exactly 1/4 the area of the round before it. If the first triangle has an area of 1, the next round adds 1/4, the round after that adds 1/16, and the next adds 1/64. Every contribution 4 times smaller than the last. Now add the pieces and watch the running total. 1, then 1 1/4, then a little more and a little more. the total creeps upward toward a single value and never crosses it, drawing closer with every round. That value is 4/3. The area of the parabola piece is exactly 4/3 of the first triangle you drew. Exactly. Not approximately, not more or less. And that word is where you must tread carefully, because you are Greek, and the Greeks do not trust infinity. Aristotle had drawn a firm line a century or so earlier. Infinity, he said, may exist as potential, but never as something completed. You may always count one number higher, always cut a line one more time, but you may never hold all the pieces at once, finished, in your hand. An actually infinite collection of steps was not mathematics. It was a kind of madness, and respectable geometry would not touch it. So Archimedes never says the forbidden thing. He never says, add infinitely many triangles. Instead, he uses a technique inherited from an earlier mathematician named Eudoxus, a technique later called the method of exhaustion, and it works, roughly speaking, like a gentle trap closing from both sides. Suppose the true area were larger than 4/3 of the triangle. Then, since the leftover slivers can be made smaller than any amount you name, enough rounds of triangles would capture more than 4/3 all by themselves, and that, he shows, can never happen. Now suppose the true area were smaller than 4/3. Then eventually the triangles, which all fit inside the shape, would overfill it, and that is absurd as well. Too big is impossible. Too small is impossible. Only one possibility survives. The area is 4/3 exactly, and infinity was never mentioned even once. Feel the quiet depth of that move. He is sneaking up on the infinite, using only finite steps, letting an endless process finish without ever calling it endless. 2,000 years before anyone writes an integral sign, without algebra, without equations, without the machinery of limits, Archimedes is doing integration. He simply has no name for it, and no general machine to hand to anyone else. Every shape must be conquered on its own, by its own bespoke miracle of geometry. He knew, privately, that there was more to his method than his formal proofs admitted. In a long letter to his friend Eratosthenes, the librarian of Alexandria, he confessed how he really found his results by imagining shapes cut into slices thinner than any blade could manage, and weighing those slices in his mind as if on a balance. Discover first, he said, prove properly afterward. That letter vanished for many centuries. Monks scraped the parchment clean and wrote a prayer book over it, and only in the year 1906 did a scholar, peering beneath the prayers, find the faint mathematics still sleeping underneath. Archimedes himself did not get to grow old in peace. When Roman soldiers finally broke into Syracuse after a long siege, he was killed in the confusion. An old man bent over a diagram, and the story is told that even the Roman general had wanted him spared. And then, something strange, almost nothing happens next. The method was too difficult, too tailored, too dependent on one man's genius, and the question of curved areas lies down and goes to sleep for nearly 2,000 years. What was missing was a bridge, a hidden connection between the problem of areas and a completely different problem about motion and change. That bridge has a name, and it is waiting for you a few chapters ahead. In the hands of two men of the 17th century who will find it separately and then quarrel over it for the rest of their lives. We will also meet these triangles again later on when we build the integral properly and give Archimedes the machinery he never had. For tonight, simply hold the one picture as it fades. A man on a warm island filling a curve with triangles, the error shrinking toward nothing, getting closer forever. That is where calculus begins. Chapter 2. Archimedes had learned to tame shapes that hold still, but motion is harder because motion never holds still at all. A circle waits patiently while you measure it. A parabola lies quietly beneath its triangles, letting itself be filled. But a runner, a falling stone, an arrow in flight, these are different creatures. By the time you have finished pointing at them, they are somewhere else. Motion slips through the fingers of geometry, and the Greeks knew this, and one Greek in particular made a whole career of saying so. His name was Zeno, and he lived in Elea, a Greek town on the southern coast of Italy, about 2 centuries before Archimedes was born. Zeno was a student of the philosopher Parmenides, who taught a strange and beautiful doctrine, that change itself is an illusion, that beneath all appearances the world is a single, still, unchanging thing. Zeno saw his task as defending his teacher, and he chose the most unsettling way imaginable. He did not argue that motion is unreal. He simply showed that whenever you try to describe motion carefully, using reason alone, you tie yourself into knots. Consider his arrow. An archer draws a bow and lets an arrow fly across a quiet field. Nothing could be more ordinary. Now, says Zeno, freeze the picture at one single instant of the flight. At that instant, the arrow occupies exactly one place, a region of space exactly its own size. It is not partly here and partly there. It is simply there, filling its own length, just as a resting arrow fills its own length on a shelf. In that frozen instant, the flying arrow is indistinguishable from an arrow lying perfectly still. And the whole flight, Zeno continues, is nothing more than a collection of such instants, one after another after another. If the arrow is at rest in every single instant, then when exactly does it ever move? Hold that question gently, the way you would hold something fragile. Do not try to answer it yet. Only notice how strange it is, how it takes the most familiar sight in the world and quietly makes it impossible. Zeno had another puzzle, even more patient. Suppose you wish to walk across a room. Before you can reach the far wall, you must first reach the halfway point. That sounds harmless enough, but before you reach the halfway point, you must reach the point halfway to it, 1/4 of the way across the room, and before that, 1/8 of the way, and before that, 1/16. However small a first step you propose, there is always an earlier step you must finish first, half its size. The short walk divides itself into infinitely many pieces, and it seems you must complete an endless list of tasks, one by one, before arriving anywhere at all. And yet you cross rooms every day of your life. You will cross one tomorrow morning without a moment of thought. Infinitely many steps, somehow completed in a few unhurried seconds. Philosophers wrestled with these riddles for centuries. Aristotle offered careful answers, drawing distinctions between different kinds of infinity, and his answers satisfied many people for a very long time. But hiding inside Zeno's puzzles, beneath all the philosophy, there is a plain mathematical question, and it is worth saying slowly, because the whole story ahead turns on it. The question is this: what is the speed of a moving thing at a single instant? We know what speed means over a stretch of time. You travel some distance, you divide it by the time it took, and the answer is your speed. 60 miles in 2 hours is 30 miles in each hour. That recipe is ancient, and it works beautifully, as long as you have a distance and a time to divide. But now ask about one instant, one frozen moment of the arrow's flight. In a single instant, the arrow travels no distance at all, and a single instant lasts no time at all. So the recipe asks you to divide 0 by 0, and that is not a number. It is not even a question. 0 divided by 0 could be anything, which is another way of saying it means nothing. The very idea of speed, the recipe itself, dissolves exactly where we want to use it, and yet the arrow plainly has a speed at each moment. You feel this in your body. A car does not only have an average speed for the whole journey. It has a speed right now, this instant, the number a needle would point to. The world clearly contains such a thing as speed at a moment. Mathematics, for 2,000 years, clearly did not. There were flickers of progress along the way, small lights in a long dusk. In the 14th century, in Paris, a gentle scholar named Nicole Oresme tried drawing pictures of motion. He would let a horizontal line stand for time flowing past, and above each moment he would raise a vertical bar whose height showed how fast something was moving just then. Faster meant taller, slower meant shorter. Speed became a shape, a little skyline of bars, and Oresme noticed something lovely. The area under that shape, the amount of surface the skyline enclosed, measured the total distance traveled. Speed drawn as a picture, and distance hiding inside it as an area. He was closer to the secret than he could possibly have known, and then his idea, like so many ideas, drifted quietly back to sleep. So the tension remained, simple and stubborn. The world moves. Everything you have ever seen has been in motion, planets and rivers and dust in sunlight. And mathematics, the most precise language human beings possess, could not say how fast anything was going at any given moment. It could only speak of averages, of distance over elapsed time, and averages blur exactly the thing we want to see. Here is what will eventually happen, told softly, in advance. Someone will find a way to divide 0 by 0 without ever actually dividing 0 by 0. That sounds like a riddle, and in a sense it is, but it is also a perfectly honest description of the central trick of everything ahead. You sneak up on the forbidden fraction. You consider tiny distances divided by tiny times, smaller and smaller, watching where the answers are heading, and you learn to name the destination without ever taking the final, illegal step. Archimedes crept up on the circle this way, with polygons. Someone will creep up on speed the same way, with shrinking slivers of time, but not yet. For now, let the arrow hang in the evening air, at rest in every instant, and somehow moving all the while. The puzzle does not need to be solved tonight. It has waited this long. It can wait a little longer, while the world slowly gathers the tools it will need. Chapter 3. The 17th century arrives, and Europe, almost without noticing, begins assembling the pieces of a machine that no one has imagined yet. The first piece comes from a French soldier and philosopher named René Descartes, a man who loved to think while lying in bed late into the morning. Descartes did something that sounds simple and changed everything. He married algebra to geometry. Picture two straight lines crossing at a right angle, one running left to right, the other running up and down like the corner of a page. Now every point on the page can be named by two numbers, how far along and how far up. A point becomes a pair of numbers, and once points have names, something remarkable follows. A curve, which is only a family of points, becomes a family of number pairs, and the rule connecting those pairs is an equation. A circle becomes an equation. A parabola becomes an equation. Every curve becomes a sentence written in algebra, and every such sentence, read backward, draws a curve. It is worth pausing on how quiet and how enormous this is. For all the centuries before, geometry was something you did with your eyes and your hands, with drawn figures and clever constructions, the way Archimedes did it in the sand. After Descartes, a shape is something you can calculate. You can ask questions about a curve without ever drawing it, just by working the algebra of its equation. The frozen world of shapes and the flowing world of symbols turn out to be a single country, seen from two sides. Descartes published this idea in the year 1637, tucked, almost casually, into an appendix at the back of a book of philosophy. The second piece comes from Descartes' rival, a lawyer in the south of France named Pierre de Fermat. Fermat was not a professional mathematician. He judged legal cases by day and did mathematics in the evenings for pleasure, scribbling his discoveries into letters and into the margins of books, often without proofs, like a man leaving small gifts along a road. And Fermat found something that should make you sit up, or would, if you were not so comfortable. He found a method for the two problems that will soon matter most: finding the tangent line that just grazes a curve at a point, and finding where a curve reaches its highest or lowest value. His method went like this. Take the point on the curve you care about. Now nudge it, ever so slightly, by a tiny amount that Fermat called E, a little whisper of a quantity. Write out the algebra for the original point and for the nudged point, and compare them. Terms cancel. Things simplify. You divide through by E, which you may do since E is not zero. And then at the very end comes the strange step. Fermat lets E vanish. He sets it aside, discards it, treats it as nothing after all, and the answer that remains is correct. The tangents are right. The high points and low points are right. The method works again and again, and Fermat never quite explains what he is doing. Is E something, or is it nothing? If it is something, you cannot simply throw it away at the end. If it is nothing, you had no right to divide by it in the middle. Fermat does both with a lawyer's calm and moves on. He is standing at the edge of the derivative, close enough to touch it, and he does not press the question. Remember that little E, sleeping in the margins. Its family will return. Meanwhile, the sky itself is handing out clues. In Prague, an astronomer named Johannes Kepler spends years buried in tables of observations, hunting for the true paths of the planets, and finds that they travel in ellipses around the sun. But he finds something subtler too. A planet does not move at a steady pace. It hurries when it is near the sun and dawdles when it is far away. And yet there is a hidden steadiness beneath the changing speed. If you draw a line from the sun to the planet and watch it sweep, that line brushes out equal areas in equal times, always, like a slow windshield wiper obeying a secret law. Notice what has happened. The mystery of a changing speed has been captured by an area, a swept surface. Areas measuring motion, exactly the shadow of what Oresme once drew, now written across the heavens. And in Italy, Galileo is rolling bronze balls down gently sloped ramps, timing them with water clocks and with his own pulse, slowing gravity down enough to study it. He finds that a falling body does not cover equal distances in equal times. In each new second, it goes farther than the second before, and the total distance grows in proportion to the square of the time. Twice the time, 4 times the distance. 3 times the time, 9 times the distance. The path of a thrown ball, he shows, is a parabola, the very curve Archimedes once measured for its own quiet sake. Nature, it turns out, keeps handing the 17th century curves and rates, curves and rates, as if repeating a hint to a student who has not yet seen the pattern. So look at the table now, everything laid out in the lamplight. Descartes has given a way to turn every curve into an equation and every equation into a curve. Fermat has a trick for tangents and for peaks, powered by a vanishing whisper called E that no one can explain. Kepler has areas that measure the motion of planets. Galileo has distances growing with the square of time, motion tamed into numbers. The area problem and the motion problem, the two ancient strangers, are lying side by side on the same table, dressed in the same new algebra. Every tool is present. Every clue is visible. What is missing is not a tool. What is missing is a person, someone who will look at all of it, the tangents and the areas, the speeds and the sweeps, and see that these are not many problems at all, but one single machine with 2 handles, each one undoing the other. 2 people, as it turns out. One of them is a quiet, difficult young man who is about to be sent home from his university because a plague is spreading through England. The other is a diplomat and philosopher who has not yet turned his mind to mathematics at all. Their story is next. There is no hurry. The candles are lit, the plague year is coming, and the greatest idea in the history of mathematics is about to occur to 2 different men, far apart, who will spend their old age at war over it. Chapter 4. Imagine you are 22 years old and the university has just closed. It is the summer of 1665 and plague is moving through England like a slow, dark tide. In Cambridge, the colleges are emptying, the lecture halls have gone quiet, and the students are scattering to their family homes. You pack your books and your notebooks, and you travel north, back to the farmhouse where you were born. The house is called Woolsthorpe, a small stone building among orchards and sheep pastures in Lincolnshire. Your name is Isaac Newton, and almost nobody in the world knows who you are. You are not yet a professor. You are not yet a legend. You are a quiet, watchful young man with a candle, a stack of paper, and suddenly, nothing but time. Let us step back now and watch him from a little distance, the way you might watch a light in a far window. The plague kept the university closed, on and off, for nearly 2 years. Newton spent those months at home with no teachers, no lectures, and no one to talk to about mathematics at all. And in that silence, something extraordinary happened. In roughly 18 months, working alone at a farmhouse desk, he built more new mathematics and physics than most scientists produce in a lifetime. He later recalled that in those days, he was in the prime of his age for invention and minded mathematics and philosophy more than at any time since. It began with a pattern. Newton had been reading the great algebra books of his day, and he noticed something hidden inside a familiar formula. There was a known rule for expanding powers of a simple sum, a rule that worked for whole numbers, 2, 3, 4, and so on. Newton asked a strange, quiet question. What if the power did not have to be a whole number at all? What if you could raise something to the power of 1/2, or a negative number, and the same pattern would still unfold, only now as a sum that went on forever? He tested it, and it worked. This became his generalized binomial theorem, and it gave him something priceless. It let him turn curved, difficult expressions into long, gentle sums of simple pieces he knew how to handle one at a time. Then came the deeper idea, the one this whole story has been walking toward. Newton began to think of mathematical quantities, not as frozen shapes on a page, but as things that flow. Picture a point gliding along a curve, the way a drop of water slides down the outside of a glass. The distance it has traveled is growing. Its height is changing. Everything about it is in motion. Newton called these flowing quantities fluents, from the Latin word for flowing. And then he asked the question that unlocked everything. At this exact instant, how fast is each quantity flowing? That instantaneous speed of flow he called a fluxion. If a fluent is the water in a filling bathtub, the fluxion is how fast the water is rising right now, at this very moment, not on average over a minute. If the fluent is the distance a carriage has covered, the fluxion is the speed the horses are making at this precise heartbeat. Newton had turned the ancient riddle of the tangent line into a question about motion, and motion was something he understood in his bones. His method for actually computing these fluxions was beautifully sly. Suppose you want to know how fast some quantity is changing at a given moment. Newton would let a tiny sliver of time pass, a sliver he wrote with a small letter O, chosen because it was almost nothing, almost a zero, but not quite. In that little breath of time, every flowing quantity changes by some small amount. He would write out the change, divide by the little o to get a rate, and then, in the final step, he would let the o fade away entirely, like a soap bubble thinning until it vanishes. What remained after the vanishing was the pure, instantaneous rate, the fluxion. Whether that vanishing step was fully honest would trouble philosophers for over a century, and we will meet that trouble later. For now, notice only that it worked, and it worked on every curve he tried. And then Newton saw something even lovelier. Remember the two ancient problems, the tangent problem and the area problem, the slope of a curve and the space beneath it. For 2,000 years they had seemed like separate mysteries. Newton realized, there in the farmhouse, that they are the same mystery seen from opposite ends. Finding how fast an area grows undoes the curve, and finding rates, run backwards, recovers areas. Each operation is the reverse of the other, the way tying and untying are reverses of each other. This is the seed of what we now call the fundamental theorem of calculus, and it is such a beautiful bridge that we will give it a whole chapter of its own later in the night. As if that were not enough for 18 quiet months, the same young man began wondering about the moon. He asked whether the force that pulls a stone toward the ground might reach all the way up, weakening with distance, and be the very thing that holds the moon in its orbit. His first rough calculation came out encouragingly close, and in between, he bought a glass prism at a country fair, darkened a room, and let a thin beam of sunlight through, discovering that white light is a braid of all the colors at once. The story of the apple belongs here, and it deserves to be told gently because it is real, just quieter than the cartoon. There was no bump on the head and no shout of discovery, but in his old age, Newton himself told visitors that the notion of gravitation came into his mind as he sat in a garden in a contemplative mood, and that it was occasioned by the fall of an apple. He watched it drop, and he wondered why apples always fall toward the center of the earth, and how far up that pull might reach. A falling apple, a patient mind, and a question allowed to ripen slowly. That is the true shape of it, and here is the strangest part of the whole plague year's story. Newton told almost no one. He wrote his method of fluxions out carefully in private tracts, and then he put the papers away. He showed pieces to a few colleagues over the years in guarded letters, sometimes even hiding claims inside coded anagrams, but he did not publish. He was thin-skinned about criticism, secretive by temperament, and in no hurry at all. The most powerful mathematical method ever devised sat locked in a drawer in England, known in full to exactly one living person for decades. And while it sat there in the dark, across the sea in Germany, a young diplomat was teaching himself mathematics at astonishing speed. He was a philosopher, a courtier, a dreamer with a genius for symbols. He was about to invent the very same calculus entirely on his own, and he would write it in a language so clear, so perfectly designed, that it is the language we still write today. Chapter 5. His name was Gottfried Wilhelm Leibniz, and he may have been the most widely gifted human being of his century. He was a lawyer, a diplomat, a historian, a philosopher, an engineer, a librarian, and eventually a mathematician, all in one restless life. In 1672, his diplomatic work carried him to Paris, then the glittering capital of European learning. He was in his mid-20s, and by the standards of the great mathematicians, he was starting absurdly late. He barely knew the modern mathematics of his day. Within about 4 years, guided by the great Dutch scientist Christian Huygens, and by his own ferocious reading, he had caught up with the frontier and then quietly walked past it. Leibniz came to mathematics carrying a very particular dream. He believed it should be possible to build a universal language of reasoning, an alphabet of human thought in which ideas could be combined as reliably as numbers are added. He imagined disagreements ending not in argument but in calculation, with both parties simply sitting down to compute the answer. That dream, in its full form, never came true, but it shaped everything he touched because it made him care, more than perhaps anyone before him, about how ideas are written down. He believed that the right symbols do not merely record thinking. The right symbols do some of the thinking for you. In Paris, in the 1670s, working independently and knowing nothing of the papers locked away in England, Leibniz found his own way to the calculus, and because of who he was, his version came dressed in notation of almost unreasonable elegance. Where Newton imagined quantities flowing in time, Leibniz imagined a curve built from infinitely small steps. He wrote dx for an infinitely small difference in x, a step along the curve too small to see. He wrote dy for the corresponding tiny difference in y, the little rise that goes with that little run, and the slope of the curve at a point became simply their ratio, dy over dx, the tiny rise divided by the tiny run. You can hear the geometry inside the symbols. The notation is a picture of the idea. For the other ancient problem, the problem of areas, Leibniz did something just as graceful. To find the area under a curve, you imagine slicing it into infinitely many slivers, each one a thin strip standing under the curve, and adding them all up. Leibniz wanted a symbol for that endless summing, so he took the letter S for sum and stretched it tall and slender. That elongated S is the integral sign, the graceful curved mark that still opens every integral written anywhere on earth. An infinite sum of infinitely thin slices captured in a single flowing gesture of the pen. It is worth pausing drowsily on why this matters so much. Newton and Leibniz discovered essentially the same machine, but Newton's version was written in dense prose and dotted letters, tangled with the language of motion and half hidden in unpublished papers. Leibniz's version was written in symbols that almost operate themselves. His notation made the rules of calculus look like simple grammar, patterns a student could learn, practice, and trust. A good notation is like a well-cut key. It fits the lock so smoothly that the door seems to open on its own. Leibniz's calculus could be taught. Newton's, for a long time, could barely be read, and Leibniz published. In 1684, he printed a short, compressed paper in a scholarly journal, laying out his new method of differences with the rules for handling dx and dy. A companion paper on the integral followed 2 years later. It was the first public appearance of calculus in the history of the world, some 20 years after Newton's plague years discoveries, but years before Newton allowed his own account into print. The brothers Bernoulli in Switzerland seized on the new method, extended it, and taught it to Europe. The machine was finally out of the drawer. Then came the quarrel, and it is a sad story, so we will tell it softly. As calculus spread, questions began to circulate. Who had truly invented it first? Newton's friends noted, correctly, that he had done his work decades earlier. Leibniz's defenders noted, also correctly, that he had discovered it on his own and had actually shared it with the world. National pride poured in like weather. English mathematicians rallied around Newton, continental mathematicians around Leibniz, and whispers of plagiarism began to travel in both directions, feeding on old letters and half-remembered meetings in London. Eventually, Leibniz, wounded, appealed to the Royal Society of London to examine the matter fairly. It was a doomed request, because the president of the Royal Society at that time was Isaac Newton himself, A committee was appointed, and in 1712 it issued a report siding entirely with Newton. What the world did not know for a long time was that the report's conclusions were largely drafted behind the scenes by Newton. The judge had written the verdict in his own case. It remains one of the strangest episodes in the history of science, this spectacle of the two greatest minds in Europe, quarreling like brothers over a shared inheritance. History, given a few centuries to breathe, reached a calmer verdict. The two men invented calculus independently. Newton found it first, in the quiet of the plague years. Leibniz found it on his own and published it first. And it is Leibniz's notation, the dx, the dy over dx, the long, graceful integral sign, that stands today on every blackboard on earth. Both things are true at once, and there was room enough in history for both men, even if there was not room enough in their lifetimes. The human cost was real, and it fell hardest on Leibniz. He spent his last years under a cloud, his reputation battered, the accusation of theft still hanging in the air. When he died in 1716, the dispute was still burning, and this man, who had corresponded with half the learned world, was buried quietly, with little ceremony. Newton outlived him by more than a decade, celebrated and knighted, yet by some accounts still nursing the old grievance to the end. There is one more gentle lesson folded into this story, and it is about tools. Out of loyalty to Newton, English mathematicians clung to his fluxions and his dot notation for roughly a century, while the rest of Europe raced ahead using Leibniz's supple symbols. British mathematics, which had led the world, drifted slowly behind, until reformers in the early 1800s finally persuaded England to adopt the continental notation. The ideas had been the same all along, only the language differed. It is a quiet reminder worth holding as you drift, that how we write our thoughts shapes how far our thoughts can travel. So there they rest, two inventors and one machine. Newton heard it as motion, quantities flowing through time. Leibniz saw it as language, infinitely small differences and infinite sums, written in perfect symbols. Two minds, one calculus. And now, with the story of its birth complete, we can finally do the gentlest thing of all. We can open the machine itself, slowly, piece by piece, and watch how it actually works. Chapter 6. Imagine you are driving at night on a long, quiet road, and the dashboard glows softly in front of you. The needle of the speedometer rests near 60, and you accept that number without thinking about it. But pause for a moment, in that warm and drowsy way you can when nothing is urgent, and ask what the number means. Speed is distance divided by time. If you cover 60 miles in 1 hour, your average speed for that hour is 60 miles per hour. That much is easy, and everyone agrees. Yet an average taken over a whole hour hides everything that happened inside the hour. You slowed for a gentle curve. You eased quietly past a sleeping town. You drifted a little faster on a long, straight stretch under the stars. The average smooths all of that away, like a tide erasing footprints. So you ask a more honest question. Not how fast over the whole hour, but how fast during this 1 minute. You measure the small distance covered in that single minute and divide by the minute. The answer is closer to the truth of the road under your wheels right now. Then you shrink the window again and ask about this 1 second. A tiny sliver of distance divided by a tiny sliver of time. Each smaller window gives you a new average, and each new average is more honest than the one before it. You can feel where this is going, the way you can feel a story leaning toward its next page. And now the strange, beautiful question at the very center of calculus. What is your speed right now, at this exact instant? An instant has no width at all. In an instant, the car covers no distance, and no time passes. 0 divided by 0, the old trap, the same shadow that troubled Zeno more than 2,000 years ago. But calculus does not step into the trap. Calculus notices something gentler and far more clever. As the windows of time shrink, the averages do not wander around at random. They settle. They drift toward one particular number and gather closer and closer around it, the way a feather settles toward the floor. That number, the value the averages are heading toward, is your speed at this instant. It is called the derivative. It is not the last average, because there is no last average. It is the destination of the averages, the place they were always going. Hold on to that one idea, because everything else in this chapter is the same idea wearing different clothes. Now let us see the very same thing as a picture, since you may see it even with your eyes closed. Imagine a smooth curve drawn across a page, rising and dipping like a hillside seen from far away. Choose one point on that curve and rest your attention there. Now choose a second point a little farther along and draw a straight line through both points. That straight line has a slope, a simple steepness, rise divided by run, the same as any ramp or staircase. It is the picture version of an average speed. It tells you how the curve behaves between the 2 points, on average, while ignoring every wiggle in between. Then comes the quiet, patient move, the same move as before. Slide the second point slowly along the curve, closer and closer to the first, and watch what happens to the line between them. With every step, the line tilts a little, adjusting itself, and its slope changes. And once again, the slopes do not wander aimlessly. They settle. They lean toward one particular value, and as the 2 points nearly touch, the line comes to rest in one final position. That resting line is called the tangent. It kisses the curve at a single point and matches its direction perfectly there. Its slope is the steepness of the curve at that one point, the derivative drawn as a picture. Speed of a car, slope of a curve, one idea in 2 costumes. Let us do one example together, slowly and gently, with no rush at all. Take the simple curve where y equals x squared, so the height above any point is that number multiplied by itself. Stand at the place where x is 3. The height there is 3 times 3, which is 9. Now take a nearby point, just a little to the right, at 3 plus a tiny nudge. Picture the nudge as something almost too small to see, a breath, a whisper of distance. The height at that nearby point is 3 plus the nudge, all multiplied by itself. If you multiply that out patiently, you get 9 plus 6 times the nudge plus the nudge times itself. So how much did the height rise between our 2 points? It rose by 6 times the nudge plus the nudge times itself, because the original 9 cancels away. And how far did we move sideways? Exactly 1 nudge. The slope of the line between the points is the rise divided by the run. And when you divide everything by the nudge, the answer comes out clean. The slope is 6 plus the nudge. That is all. 6 plus whatever tiny nudge we happen to choose. Now let the nudge fade. Let it grow smaller and smaller, softer and softer, like a sound disappearing down a hallway. 6 plus the nudge drifts toward 6 plus nothing, which is simply 6. The slopes settle on 6, so the steepness of the curve y equals x squared at the point where x is 3 is exactly 6. And notice something lovely. 6 is 2 times 3. If you repeat the whole gentle argument at any other place, the same pattern appears. The derivative of x squared is 2x everywhere, at every point along the curve. From one patient calculation, a rule for infinitely many points. So what is a derivative out in the world away from curves on a page? It is sensitivity. It measures how much the output cares about the input, how strongly one thing responds when another thing changes a little. When the input is time and the output is position, the derivative is velocity. When the output is the size of a population, the derivative is its growth rate. When the output is the cost of making things, economists call the derivative marginal cost, the price of making just one more. When you ride a bicycle up a hill, the derivative of the hill is the steepness you feel in your legs. Anything that changes has a derivative hiding inside it, a number saying how fast, how steep, how sensitive, right now. And notice what the limit has quietly done for us. It has answered Zeno politely and completely. We never divide 0 by 0. Not once. We only look at honest ratios, real distances over real times, and we watch where those ratios are heading as the window shrinks. The destination is well defined, even though the journey never ends. We name the destination and we call it the answer. That naming, humble as it sounds, is the key that took 2,000 years to cut. That is the derivative's personality, and it is worth resting with for a moment. It turns curves into slopes. It turns positions into velocities. It takes soft, sliding, continuous change, the kind that used to defeat every philosopher who touched it, and turns it into a single number you can compute, compare, and trust. Half of the machine is now open in front of you. The other half is waiting, and it begins with a very old friend. Chapter 7. Do you remember, from the very beginning of this story, the old man in Syracuse filling a curved shape with triangles? Archimedes slid triangle after triangle under the arch of a parabola, each one smaller than the last, and added them up and trusted the pattern. He could not finish the sum because no one can place infinitely many triangles. Yet he could see where the sum was going, and he had the courage to call that destination the answer. We promised back then that we would return to him. This chapter is the keeping of that promise, because the second half of calculus is his idea, grown up and given a name. Here is the problem this half of the machine was built to solve. The derivative took a total and asked for a rate. Now we ask the opposite. Suppose you know the rate at every moment and you want the total. Imagine you rode in a car all night and you never watched the road, only the speedometer. You know how fast you were going at every instant, but nobody told you the distance. Could you recover it? Or picture a tap filling a bath while you doze, its flow rising and falling gently. Knowing the flow at each moment, could you say how much water has gathered? or simply this, the oldest version of all. A curve drawn over a flat line, and the question of how much area lies beneath it. All three questions are secretly the same question. They are questions of accumulation, of adding up a quantity that never holds still. And here is the move, the one Archimedes would recognize with a slow smile. Slice the night into thin strips of time. In each thin strip, tell a small, harmless lie. Pretend the speed was constant during that strip, frozen at whatever value it had. For a constant speed, the arithmetic is easy. Just speed multiplied by the width of the strip, one little rectangle of distance. Do this for every strip and add all the little rectangles together. The sum is not the exact answer, because the speed was never really constant, but it is close, and you already know what to do with close. Make the strips thinner. Where you had 60 strips, take 600, then 6,000, each one narrower than a breath. With every refinement, the small lies shrink, because the speed has less room to change inside a thinner strip. If you draw this under a curve, you see a staircase of rectangles pressed up under the arch, and as the strips narrow, the staircase softens and leans into the curve, hugging it closer and closer until your eye can barely tell them apart. It is the same picture Archimedes saw in the sand, only with rectangles in place of triangles, and the same patient trust carrying it forward. And the sums, just like the slopes in the last chapter, do not wander. They settle. They drift toward one particular number and gather around it. That number, the destination of the sums, is called the integral. It is the exact area, the exact distance, the exact total, reached by an endless staircase of honest approximations. Much later, a gentle German mathematician named Bernhard Riemann tidied this idea up, saying carefully which curves allow it and why the answer does not depend on how you slice, whether your strips are all the same width or a little uneven, whether you measure each rectangle from the left edge of its strip or the right, the sums still settle on the same quiet number. That steadiness is what makes the integral trustworthy, and Riemann was the one who proved it holds. So the rectangles carry his name now, and we speak of Riemann sums, though the heart of it is pure Archimedes, 2,000 years older than its label. Leibniz, of course, gave the idea its costume. You have already seen his sign for the integral, that long, flowing letter S, stretched tall and thin, an S for sum. That is all the famous symbol means, an S for sum, elongated as if it were exhaling. When mathematicians write it, they are saying softly, add up all the slivers, all the infinitely thin slices of this quantity, from here to there, and tell me what they come to. The notation is a picture of the process, an infinite sum of infinitely thin contributions, written in a single relaxed stroke. And what are integrals? Out in the world. They are how you get a total from a rate. Distance is the integral of speed, the whole journey assembled from moment after moment of motion. Energy is the integral of power. Everything, a lamp consumed through the night, gathered from its steady little draw. In a hospital, the dose a patient receives from a slow drip is the integral of the flow, drop after drop accumulating into care. The rain that fell on your roof through a long, soft storm is the integral of the rainfall rate, gathered hour by hour into one measure. And the area of any honest shape, however curved or strange, is an integral, sliced into slivers and summed. Whenever something arrives little by little, and you want to know how much has arrived altogether, you are asking for an integral, whether you use the word or not. The world accumulates constantly, quietly, in rivers and bank accounts and growing children, and the integral is simply the mathematics of that gathering. Notice, too, how familiar the final move felt. In the last chapter, the shrinking windows gave averages that settled toward one number, and we called it the derivative. In this chapter, the thinning strips gave sums that settled toward one number, and we called it the integral. Both halves of calculus rest on the same quiet trick, the limit, the art of naming a destination you can approach but never quite reach. Once you learned it for slopes, you already owned it for areas. That is why this half of the story could be told more briefly. You did most of the work while learning the first half without knowing you were doing it. Now lie still for a moment and notice what you can already feel because you have earned it. The derivative takes a total and breaks it apart, asking how fast it changes at each instant. The integral takes those instants and gathers them back together, rebuilding the total from its rates. One takes apart, the other reassembles. One divides, the other sums. They face each other like two mirrored staircases, one leading down into the moment, the other leading back up into the whole. It would be almost too perfect if these two operations, invented for different problems in different centuries, turned out to be one another in reverse. It would mean that slope and area, a steepness and a shaded region, are secretly two ends of the same thread. That feeling you have right now, that quiet suspicion of a hidden symmetry, is not a trick of the late hour. It is real, and it has a name, and it is the most important theorem in this entire story. It is waiting for us, patiently, in the very next chapter, Chapter 8. We have now walked two very old roads, and tonight it is time to notice something quiet and astonishing about them. The first road was the tangent problem, the question of steepness, the question of how fast something is changing at a single instant. The second road was the area problem, the question of how much has gathered, of how much a curved shape can hold. For 2,000 years, these were simply two different problems, filed in two different drawers of the human mind. The Greeks knew them both. Archimedes himself worked on tangents in one investigation and areas in another, and even he never suspected a connection. Slopes felt like a question about direction, about which way a curve is leaning. Areas felt like a question about amount, about how much space is enclosed. Nobody imagined that they were secretly the same subject wearing two different coats, and yet they are. This is the fundamental theorem of calculus, and it says something almost too simple to believe. Finding slopes and finding areas are inverse operations. Each one undoes the other, the way addition undoes subtraction, the way unpacking a box undoes the packing of it. If you take a curve and patiently accumulate the area beneath it, and then you ask how fast that accumulated area is growing, you get back the very curve you started with. The derivative unwinds the integral. The integral rewinds the derivative. Two ancient mysteries, carried separately for 20 centuries, and each one turns out to be The other one read backwards. If that feels abstract, come and sit in the car with me again, because you already own this idea. On the dashboard, there are 2 gauges, and we have met them both. The speedometer tells you how fast you are going right now, in this very moment. The odometer tells you how far you have traveled in total, all the moments added together. Now notice, gently, what each gauge is doing with the other one's information. The speedometer is the derivative of the odometer, because speed is nothing more than the rate at which your distance is growing. If the odometer is climbing quickly, your speed is high, and if it is barely creeping, your speed is low. And the odometer is the integral of the speedometer, because total distance is nothing more than your speed gathered up, moment by moment, across the entire journey. 2 gauges on one dashboard, describing one single trip. They are reading the same motion in 2 different languages, and the fundamental theorem is the translation between them. Every drive you have ever taken has been a quiet demonstration of the deepest result in calculus. Here is the intuition at the very heart of it, and I want to say it slowly, because this one idea is the whole theorem. Imagine sweeping out the area under a curve from left to right, the way a slow tide creeps up a beach. Your sweeping edge is a vertical line, moving gently rightward, and behind it, the collected area keeps growing. Now ask the calculus question. How fast is that area growing right at this moment? Well, look at where your sweeping edge is standing. If the curve is tall right there, then each small step to the right adds a tall, thin strip, and the area grows quickly. If the curve is low right there, each small step adds only a short little sliver, and the area grows slowly. So the rate at which the area grows is exactly the height of the curve at that spot. That sentence is the fundamental theorem of calculus. The rate of change of the accumulated area is the original function itself. Accumulation and rate of change are 2 views of one thing, like a mountain seen from the east and from the west. Now consider what this discovery bought humanity, because it was not a small purchase. Remember how painful areas used to be. To measure a curved region, you had to slice it into hundreds of rectangles, add them all up, then slice thinner and add again, chasing an infinite process toward its limit. Archimedes needed genius and years for a single shape. The fundamental theorem says you never have to do that again, so long as you can run the slope machine in reverse. Find a function whose derivative is your curve. Such a function is called an antiderivative, a name that simply means the thing whose slope story you already know. Then evaluate that antiderivative at the 2 ends of your region, subtract one value from the other, and you are done. The infinite sum has already been carried out for you, folded silently inside that subtraction. A problem that had resisted the best minds of antiquity collapses into a line or 2 of ordinary algebra. It is as if humanity had been carrying water up a hill by the spoonful, and someone quietly pointed out the existence of a pipe. Newton saw this bridge, and across the sea Leibniz saw it too, each in his own way, each with his own notation. This shared vision is why their machine changed the world. Instead of remaining a curiosity in a scholar's drawer, astronomers could now compute the paths of comets. Engineers could sum up forces along a beam without a lifetime of slicing. The two oldest problems in mathematics had been revealed as one, and the doors that opened have never closed since. But listen closely, because underneath all this triumph there was a whisper. The whole magnificent machine was built on talk of infinitely small quantities, those ghostly slivers that were treated as something one moment and as nothing the next. Nobody, not even Newton, not even Leibniz, could say precisely what they were. The bridge stood, and the traffic across it was glorious, but no one had truly inspected the foundations. And one sharp-eyed bishop was about to kneel down, look underneath, and call the whole beautiful thing a fraud. Chapter 9. The year is 1734, and the challenger is not a mathematician at all. George Berkeley is a bishop in Ireland, a philosopher, a careful and elegant writer. He has grown tired of hearing certain scientific men mock religious faith as unreasonable, and so he decides to examine their own reasoning, the calculus itself, with the coldest eye he can manage. He publishes a short book called The Analyst, and it is one of the great pieces of intellectual demolition ever written. His attack is very simple, and that is what makes it so devastating. Consider those vanishing increments, the little quantities at the heart of every derivative. When it is convenient, the mathematicians treat them as something. They divide by them, which you may only do with a quantity that is not zero. Then, a line later, when it becomes convenient, they treat them as nothing. They discard them from the answer as if they had never existed. Berkeley says, calmly and lethally, that you cannot have it both ways. Either the increment is something, in which case you may divide by it but not throw it away, or it is nothing, in which case you may throw it away but you were never allowed to divide. And then he delivers the phrase that has echoed for 3 centuries. These increments, he says, are neither finite quantities nor quantities infinitely small, nor yet nothing. May we not call them the ghosts of departed quantities? And here is the uncomfortable truth that mathematics had to sit with. He was right. The foundations really were mush. The explanations offered by the followers of Newton and Leibniz were circular, or vague, or quietly contradictory, exactly as Berkeley charged. And yet, all the while, the answers kept coming out true. Bridges designed with calculus stood firm. Planets arrived where calculus said they would arrive, night after night, year after year. Tides, pendulums, cannonballs, comets, all of them obeyed. It was the strangest situation in the history of thought. Humanity possessed a machine that worked flawlessly, and no one on earth could explain why it was allowed to work. The repair took more than 100 years, and it is best told as a relay race, one careful runner handing the baton to the next. The first great runner is Augustin Louis Cauchy in the 1820s in Paris. Cauchy's idea was to stop talking about infinitely small quantities altogether and to rebuild everything on the notion of a limit. A limit is not a mysterious dust speck smaller than every number. A limit is a destination. It is the value that a process approaches and approaches and approaches, coming as close as anyone could ever demand. The derivative became the limit of ordinary slopes over shrinking intervals, each of them a perfectly honest finite quantity. Nothing ever has to be infinitely small. Things only have to get closer and closer to a clearly named target, but the word closer was still soft, still leaning on intuition, and the next runner made it exact. His name was Karl Weierstrass, and his answer is the famous epsilon and delta, which sounds forbidding and is actually just a game. I will explain it once, gently, and then we can let it rest. Suppose I claim that a process has a certain limit. You are the skeptic, so you issue a challenge. You name a tolerance, any tolerance you like, and we call it epsilon. You say, I demand that the output stay within epsilon of the target. My job is to answer with a distance of my own, called delta. I say, as long as the input stays within delta of its mark, the output will stay within your epsilon. I promise. If I can always keep that promise, no matter how tiny an epsilon you name, then the limit is real, and nothing further can be asked. Notice what has happened. There are no infinitely small numbers anywhere in the game. There are only ordinary numbers and promises about closeness, promises that can always be kept. Berkeley's ghosts were not defended in the end. They were simply dissolved, replaced by a challenge game that a skeptic can never win against the truth. The baton passed once more to Bernhard Riemann, who did for the integral what the others had done for the derivative. He said precisely what it means for all those slicing sums to settle down to a single value, and precisely which curves can honestly be said to have an area at all. The word integral, which had floated on intuition since Leibniz, finally stood on ground that could bear any weight, and rigor, once it arrived, revealed some very strange creatures living in the house that intuition had built. Weierstrass himself constructed a curve that is continuous everywhere, a single unbroken thread you could trace without lifting your pen, and yet so jagged that it has a corner at every single point. Zoom in anywhere, as far as you like, and it never smooths out. It has no tangent line anywhere, which means the slope machine fails at every point of an unbroken curve. It is like a coastline that stays crinkled no matter how closely you look. For a century, everyone had quietly assumed such a thing was impossible. You do not need to picture it precisely tonight. Just hold it as a bedtime curiosity, a reminder that the world of mathematics is stranger and richer than our comfortable pictures of it. There is a soft lesson folded into this whole story, and it is worth carrying into sleep. Mathematics can run on pure intuition for a very long time, for a century, even two, producing true and useful answers the entire way. But eventually it pays its debts. Eventually someone asks the childlike question, what exactly do you mean? And the answer has to be built, stone by stone, beneath a structure that was already standing. Berkeley thought he was tearing calculus down. In truth, he did it the greatest favor imaginable, because the repaired foundations turned out to be far more beautiful than the ghosts they replaced. And yet one more debt remained on the books, one the bishop never even mentioned. Calculus still leaned, everywhere, on infinite sums, on the idea of adding forever and arriving somewhere finite. That was the very thing Zeno had worried about more than 2,000 years before, standing beside his runner, who could seemingly never finish the race. Whether an infinite pile of pieces can truly settle into a single quiet number, and how mathematics finally learned to say yes, and sometimes no, that is the next chapter. Chapter 10. For most of this story, Zeno has been waiting in the doorway, patient in the way only ghosts are patient. Almost 25 centuries ago, he argued that an arrow could never truly reach its target. First, it must cross half the distance, then half of what remains, then half of that, and so on without end. Infinitely many steps, he said, and no one can ever finish infinitely many steps. Every chapter so far has quietly borrowed against his question. Tonight, at last, we pay the debt. Look closely at the sum he was worried about. 1/2 plus 1/4 plus 1/8 plus 1/16, and onward forever, each piece half the one before. Add the first 2 pieces, and the running total is 3/4. Add the third, and it becomes 7/8. Add the fourth, and it becomes 15/16. You can feel the pattern breathing. Each new piece carries you exactly halfway from where you stand to one. You never leap past one, and you never settle for anything less. The running totals crowd closer and closer, and the only number they crowd around is 1. Here is the quiet insight that the age of rigor made precise. Nobody actually adds infinitely many numbers, one after another, like an immortal accountant who never sleeps. We add finitely many, watch where the running total is heading, and ask whether it settles. If the totals settle toward a single value, in the careful epsilon sense of the last chapter, we call that value the sum. An infinite sum is simply a limit wearing a new coat, and this particular sum settles at exactly 1, not almost 1. Not 1 give or take a ghost, exactly 1. So the arrow lands. Infinitely many stages fit inside one finite flight, because the stages themselves shrink quickly enough. Zeno was right that there are infinitely many steps. He was wrong that infinitely many steps must take forever. Each half of the journey takes half the time, and those slivers of time add up to something finite too. That is the whole resolution, and it took more than 2,000 years to say it this cleanly. Mathematicians call such an endless sum a series, and when the running total settles, they say the series converges. It is a gentle word. The terms arrive one by one, each smaller, each mattering less, and the total drifts into place like sediment settling through still water. But not every infinite sum is so kind, and it matters to know the difference. Consider 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, onward forever. This is called the harmonic series, after the harmonics of a vibrating string. Its terms shrink towards 0, so you might expect the total to settle somewhere reasonable. It does not. It creeps upward forever, slower and slower, but it never stops climbing. Given enough terms, it passes 10. Given unimaginably many more, it passes 100. Given more terms than there are atoms in the visible universe, it has still only cleared a modest hill, and still it climbs. Nicole Oresme, the same gentle Parisian scholar who once drew speed as a skyline of bars, saw why, 7 centuries ago, with an argument you can hold while half asleep. Group the terms. 1/3 plus 1/4 is more than 1/2. The next 4 terms, taken together, are also more than 1/2. The next 8 terms, again, more than 1/2. The groups keep coming forever, each contributing at least another half, and infinitely many halves pile up past any ceiling you name. The harmonic series is a walker on an endless slope that grows ever gentler but never quite flattens, always rising, never arriving. It may be the sleepiest image in all of mathematics, ever slower, ever upward, all night long. So some series settle and some drift away, and the difference is a matter of speed. Halving at every step is fast enough. Shrinking like those harmonic fractions is not quite fast enough. A good part of the 19th century was spent charting exactly where that boundary lies, one careful test at a time. Now for the crown jewel, the reason this chapter exists. It is called a Taylor series, after Brooke Taylor, though many hands shaped it. The idea sounds almost too generous to be true. Take a complicated function, something curved and mysterious, like the sine wave that rises and falls forever. Now rebuild it, exactly, out of the simplest ingredients arithmetic owns. Powers of a number, multiplied by clean fractions, added one by one. Forever, call your number x, some small angle. Then the sign of x begins as x itself. Subtract a small correction, x times x times x, divided by 6. Add back a smaller correction, the fifth power of x, divided by 120. Subtract a correction smaller still, and continue forever, each new term fainter than the last. Cut the recipe off after only a handful of terms, and you have the sign to more decimal places than any carpenter or astronomer will ever need. This is how your calculator knows the sign of an angle. It does not keep some vast table hidden in its memory, and it does not draw tiny triangles in the dark. It adds up a few Taylor terms, multiplying and adding, which is all a machine really knows how to do, and the right answer quietly assembles itself out of fractions. Something else lovely hides here. Pi, the most famously unruly number, the ratio no fraction can ever capture, emerges from the tidiest fractions imaginable. Leibniz himself found that pi divided by 4 equals 1 minus 1/3 plus 1/5 minus 1/7 plus alternating forever. The total drifts down, drifts up, each swing smaller than the last, closing in like a slow pendulum settling to rest. It settles far too slowly to be practical, and nobody minds. What matters is that the wildest constant in mathematics answers to an endless sum of odd fractions. There is a way of hearing all this that suits the hour. A function, seen through its Taylor series, is a recipe with infinitely many ingredients, each gentler than the one before. The first term does most of the work. The second refines it. The third barely whispers, and the ones after that are corrections to corrections, fainter and fainter without end. It is the same taste as falling asleep. The first thought carries you most of the way down. Each following thought matters a little less. And the sum of all that fading is something whole. One more breath for a promise the future will keep. A French engineer named Joseph Fourier, studying how heat seeps through metal, later found that functions can be rebuilt from waves instead of powers. Gentle signs layered upon signs, heat, sound, and eventually the music playing softly on your phone all speak his language. That is all we will say tonight. It is enough to know the door is there. Step back once before we turn. Everything so far, derivatives, integrals, limits, series, has been description. We watch the world change, and we describe that change more and more finely. The last great move of calculus is to turn this around. We stop describing change, and we let a rule of change Describe the world. That is where the planets come from. And it gets the next chapter. Chapter 11. Every equation you met in school was a kind of hiding game. Some number was concealed, and solving meant finding it. A differential equation is a different creature altogether, and it is the closest mathematics comes to speaking nature's own grammar. It does not tell you the answer. It tells you the rule of change, and then it asks a question. What kind of world obeys this rule? That sounds abstract. So let us put a cup of tea on your nightstand. It is too hot to drink, and you are too comfortable to reach for it anyway. Newton himself noticed what the tea does. It cools quickly at first, while it is far hotter than the room, and more slowly as it settles toward the room's own temperature. The whole behavior fits inside one small law. The tea cools at a rate proportional to how much hotter it is than the room. That single sentence is a differential equation. It never mentions what the temperature will be at midnight. It only says how the temperature is changing at every moment, all night. But here is the wonder. Solve that equation, run the rule through the machinery of calculus, and the tea's entire night is written out in advance. A smooth, gentle slide toward the temperature of the room, steep at first, then flatter still, never quite arriving, always closer. Check the cup at midnight or at 4 a.m, and the curve already knew. One small law on a nightstand, and the whole night unfolds from it. Populations obey a cousin of the same law, pointed the other way. If each member of a colony adds new members at a steady rate, the colony grows in proportion to its own size. The more there are, the faster there are more. Solve the rule, and out comes exponential growth, the famous upward sweep. Add a small term for crowding, for food that runs short, and the sweep bends into a graceful curve that rises and then eases toward a ceiling. Algae in a pond and rumors in a town both follow that gentle shape. Or consider a pendulum swinging in the dark inside a grandfather clock. The rule is simple. The farther the weight swings from center, the more strongly it is pulled back toward home. Ask what motion obeys that rule, and the answer is a sway. Back and forth, over and over, and its shape traced out in time is exactly the sine wave from the last chapter. Nobody invited sine. It appears because it must, because sine is what that rule sounds like when you let it speak. Differential equations are full of such moments where a shape you met elsewhere walks in as if it had always lived there. Even the rain obeys. A raindrop falls, pulled downward by gravity, while the air resists it, pressing back harder the faster it moves. Somewhere the two influences balance, and the drop stops speeding up. It settles at a gentle terminal speed, and simply rides the rest of the way down. That is why rain arrives as a patter on the roof and not as something fierce. Every falling drop is a small differential equation, solved billions of times over on every rainy night, and the solution is mercy. Now replay Newton's triumph in this language, because this is what it truly was. Gravity, he said, is a rule of change. Every mass pulls on every other more strongly the closer they are, and that pull reshapes their motion moment by moment. He never claimed to know why the pull exists. He simply wrote the rule, fed it into his own calculus, and asked what paths obey it. Out fell the ellipses, Kepler had spent years coaxing that shape out of tables of observations, point by patient point. From Newton's one small rule, the ellipses simply emerged, along with the timing of the orbits, all of it, as consequences. His friend Edmund Halley trusted this grammar enough to bet across his own lifetime. Studying old records, he noticed a bright comet returning roughly every 76 years and argued it was one visitor riding a long ellipse. He predicted its next return decades ahead, knowing he would not live to see it. In 1759, the comet came back, close to schedule, and it has carried his name ever since. A rule of change, solved on paper, had reached half a century into the future and been right. Two more equations deserve to have their names spoken softly, because so much of physics lives inside them. The heat equation describes warmth spreading through a wall on a winter night, sharp differences relaxing into smoothness, everything hot leaking gently toward everything cold. The wave equation describes a plucked string, a disturbance that travels, reflects, and rings, and it describes sound in air just as well. Fourier's waves from the last chapter were invented for exactly these two. Between them, warmth and music, they are the great old classics of the subject. And now the honest confession, the one mathematicians took a long time to make out loud. Most differential equations cannot be solved with formulas at all, not because no one has been clever enough yet. For most of them, no formula of the familiar kind exists to be found. Three stars pulling on one another as they drift, the weather above one small island, water swirling gently down a drain. We can write the rules for each of these in a line or two. We cannot unwind them by hand. Nature, it turns out, is fond of writing sentences in her own grammar that we can read but never quite translate. So we do the humble thing, and it is one of the most useful ideas anyone owns. We approximate, step by tiny step. Start where you are. Ask the rule which way things are changing right now. Take a tiny step in that direction. Then ask again and step again and again, thousands upon thousands of times, letting the rule steer at every step. Each step is slightly wrong, but if the steps are small enough, the errors stay gentle, and the path you trace hugs the true one. Euler was doing this by hand in the 1700s, patiently, one arithmetic step at a time. Hold that image as the chapter closes. A path built from tiny straight steps, each one guided by the rule, curving only because the rule keeps gently correcting it. By hand, an evening's work buys you a few dozen steps. But imagine something that never tires, never loses its place, and can take those tiny steps billions of times in a single second. Machines like that were eventually built, and when they were set loose on nature's unsolvable sentences, whole new worlds opened. That story gets the next chapter. Chapter 12. If all of this sounds like history, like something kept behind glass in a museum, stay with me a little longer. Calculus did not retire when its inventors died. It moved quietly into the machines around you, and it has been running your ordinary day since before you woke this morning. So let us take a slow tour of the invisible engine, room by room, while you rest. Begin with the phone lying somewhere near your bed. When it finds your place on a map, it is listening to satellites far overhead, each one carrying an atomic clock. Your phone measures tiny differences in the arrival times of their signals, and from those differences, it works out where on Earth you are. To know where each satellite sits, the system integrates its orbit forward, moment by moment, just as we once integrated a falling apple. And there is a stranger correction hiding inside. Clocks in orbit run slightly fast compared with clocks on the ground because they sit higher in Earth's gravity, an effect their great orbital speed only partly offsets. The drift is about 38 millionths of a second every day, which sounds like nothing at all. Left uncorrected, it would push your position off by miles within a single day. Einstein's equations, which are calculus through and through, quietly repair that drift every moment. Your phone does relativity before breakfast and never once mentions it. While you sleep tonight, supercomputers will be stepping the whole atmosphere forward in time. The air is described by equations of change, how pressure pushes wind, how heat rises, how moisture gathers itself into cloud. Nobody can solve those equations by hand, just as we confessed in the last chapter. So the machines cut the sky into millions of small boxes and take tiny steps over and over all night long. Tomorrow's forecast is a giant differential equation that was patiently walked forward while the town slept. When someone says rain by afternoon, you are hearing the far end of a very long integration. If you have ever taken medicine every so many hours, you have followed the instructions of a derivative. A drug in the bloodstream fades at a rate proportional to how much is present, so its amount falls along a gentle, predictable curve. Doctors speak of a half-life, the time it takes for half of a dose to fade away. Choose the dose and the timing well, and the level in the blood stays inside a band that is safe and useful. The schedule printed on the bottle is a solved equation of change, dressed up in plain words. Before a new car is ever built, it crashes thousands of times inside a computer. Engineers divide its body into millions of tiny pieces, and each piece obeys the laws of stress and motion. The simulation folds the metal derivative by derivative in slow motion until the front of the car learns to crumple in exactly the way that shelters the people inside. The soft, sacrificial shape of a modern car was drawn by calculus, one tiny step at a time. Money joins the tour as well, and it brings along a famous guest. In the late 1600s, Jacob Bernoulli asked a simple question about interest. Suppose one coin earns 100% interest in a year. Paid once at the end, it becomes 2 coins. Paid in 2 half-yearly installments, each earning upon the last, it becomes 2 coins and a quarter. Paid monthly, it grows a little more, and paid daily a little more still. You might expect that compounding every single instant would make it grow without end. It does not. The value creeps upward toward a ceiling it can never pass, a number a little beyond 2 7/10. Written out, it begins 2.71828, and it runs on forever without repeating. Mathematicians call it E, and it is the natural number of growth feeding on itself. Wherever something grows at a rate proportional to its own size, savings, populations, a rumor moving through a town, the number E is quietly in charge. Continuous growth, it turns out, has a personality, and E is its name. Look around the rest of an ordinary day, and the engine is everywhere. The wing of every airplane you have ever ridden was shaped by the equations of flowing air. The bridge you cross carries loads that engineers integrated across the whole span before a single cable was hung. The power grid balances itself every second of every day, matching electricity made to electricity used, holding its rhythm steady while machines watch the rates of change. None of this asks for your attention. It simply works silently underneath everything, and when a rocket climbs, it obeys an insight gentler than you might expect. Konstantin Tsiolkovsky, a nearly deaf school teacher in rural Russia, understood it around the turn of the 20th century. A rocket is a machine that loses weight as it works. It throws burned fuel out behind itself, and with every passing moment, it becomes lighter. So the same push lifts it a little more easily. Gathering up all those moments of changing mass takes an integral, and the final speed depends on how much of the ship began as fuel. Every launch you have ever watched was quietly following the handwritten calculus of a country school teacher. The newest tenet in the engine room is machine learning. A modern neural network is a vast mathematical function with billions of adjustable dials. It learns by making guesses, measuring its error, and asking, for every single dial, the oldest question in this whole story. If I turn this a little, does the error rise or does it fall? That question is a derivative and nothing more. The network treats its error as a landscape of hills and valleys, feels the slope beneath its feet, and takes one small step downhill. The method is called gradient descent, and the slope comes from the chain rule, passed backward through every layer. Repeat that small downhill step millions upon millions of times, and the machine slowly learns to speak, to see, to translate. Every modern artificial intelligence is, underneath it all, Newton and Leibniz's machine, running at unimaginable speed. Newton began this subject while hiding from a plague, on a quiet farm, filling notebooks nobody had asked him to fill. 3.5 centuries later, the mathematics of that plague year reads your voice, lands your flights, and steadies the light above your bed. You have been living inside calculus all along. Tonight, at least, you know the name of the engine. Chapter 13. After so much history, you might assume calculus is finished, a cathedral long since built and locked. It is not. At its edges, the subject is still alive, still strange, and still surprising the people who know it best. Let me show you a few of the wild places. Gently, while the night grows deeper. In the winter of 1961, a meteorologist named Edward Lorenz was running a small weather model on an early computer. 12 equations of change, a toy atmosphere, looping quietly inside a machine that filled half a room. One day he wanted to look again at a particular run, so he restarted it partway through, typing in numbers from a printout. The printout showed 3 decimal places, while the machine had been keeping 6. The difference was smaller than 1 part in 1,000, a rounding, a breath. The new weather followed the old for a little while, then drifted, then became another weather entirely. Lorenz had stumbled onto something profound in that small accident. There are systems whose rules of change we know perfectly, and whose distant futures we still cannot predict. The tiniest difference in where you begin grows and grows until it rewrites everything downstream. He later asked, in the title of a lecture, whether the flap of a butterfly's wings in Brazil could set off a tornado in Texas. This is called chaos, and it may sound unsettling, but hear it as wonder instead. Calculus did not fail here. Calculus is how we discovered that the world keeps some of its future genuinely private. Weather can be foreseen for days but not for months, no matter how large our computers grow. The equations themselves are telling us where the horizon of knowing lies, and that too is knowledge, honest and hard-won. There is something almost restful in it if you let there be. The universe follows its rules, exactly, and still it keeps a little mystery, the way a good story keeps its ending. There are also questions that sound like jokes and turn out to be fields. In 1695, a colleague wrote to Leibniz and asked what a derivative of order 1/2 could possibly mean. Not the first derivative, not the second, but something in between, half a step of change. Leibniz replied that it seemed a paradox from which useful consequences would one day be drawn. 3 centuries later, he was proven right. Fractional calculus is now a real working subject, and its strange half-derivatives describe materials that remember. Certain gels and polymers and living tissues respond not only to how they are being stretched right now, but to everything that has been done to them before. An ordinary derivative sees only the present instant. A fractional derivative carries a soft, fading memory of the past, which is exactly what such materials seem to need. A question asked as a curiosity in a letter became, very slowly, a tool for describing things that do not forget. Then there is the quiet pardon of some very old ghosts. Early calculus leaned on infinitely small quantities, and for 2 centuries, critics mocked them as ghosts, since nobody could say what they were. The 19th century swept them away and rebuilt everything on limits, as we have seen. But in the 1960s, a logician named Abraham Robinson did something remarkable. Using the modern machinery of mathematical logic, he built a number system in which infinitesimals genuinely exist. They are called hyperreal numbers, quantities smaller than every ordinary fraction, yet still not zero, obeying a consistent and rigorous arithmetic. Within Robinson's system, you can do calculus the way Leibniz dreamed of doing it, sliding along curves in truly infinitesimal steps, and every result is fully justified. Nothing about the old calculus changes. It is simply a second road up the same mountain, and it shows that the founder's instincts were sound all along. Leibniz's ghosts were pardoned 3 centuries later by a court he could never have imagined. Meanwhile, the frontier of computation keeps pushing into places no pencil will ever reach. Einstein described gravity with equations of change so tangled that exact solutions are rare treasures. For decades, nobody could say precisely what happens when 2 black holes spiral into one another. Then supercomputers learned to take Einstein's equations step by tiny step, the same patient trick we met 2 chapters ago. The simulations predicted a signal, a ripple in space itself, rising in pitch like a bird's note as the 2 holes finally merged. In September of 2015, enormous detectors on Earth felt exactly that chirp arrive, a tremor from more than 1 billion light-years away. The measured wave matched the computed shape, curve against curve, as if the universe had checked the homework and found it correct. Calculus walked forward numerically through curved space-time, had told us what a cosmic collision would sound like before we ever heard one. And some of the oldest equations still hold unopened rooms. In the 1800s, Claude Navier and George Stokes wrote down the equations of flowing water and moving air. They govern every river, every breath of wind, the cream curling into a cup of coffee, and the weather models we met an hour ago. Engineers trust them daily, and they have never let us down. Yet nobody has proven that their solutions always behave, that a smooth flow can never twist itself into an impossible spike in a finite time. At the turn of this century, that question was placed among 7 famous problems, with a prize of $1 million waiting for a proof. The money has waited ever since, and the money is not really the point. The point is the humbling fact that the mathematics of an ordinary stream still guards a secret at its center. So the story you have been hearing tonight is not a finished monument. It is a living language, still being written, with settled old chapters and wide-open new ones. Somewhere tonight, a student is puzzling over a flow that will not behave, and a computer is stepping some impossible equation patiently toward morning. One short chapter remains now, and it will ask nothing more of you. It holds no new idea to learn, no final effort to make. It is only the whole story gathered up and seen at once, slowly, from exactly where you are, resting on the pillow. Chapter 14. We have walked a long way tonight, and now, before sleep takes the rest of you, let us turn around. Look back down the whole path, slowly, and notice something quiet and surprising. It was never many ideas. It was one idea wearing different clothes in different centuries. The idea was simple and almost shy. When something infinite frightens you, do not fight it. Approach it. Get closer and closer and closer, and watch where the closeness is heading. That patient watching has a name. We call it the limit. Everything else in this long story was the limit, learning new work to do. Archimedes knew it before it had a name. He leaned his triangles into the curve of the parabola, one generation after another, each smaller than the last. The slivers of space left over kept shrinking toward nothing, and the total kept settling toward one steady value. He trusted where the closeness was heading, and he was right, and he was 2,000 years early. Zeno's arrow flies for the same reason. The flight can be cut into infinitely many pieces, each one real, each one smaller than the one before, and yet infinitely many steps can add up to something finite. The halves and quarters and eighths pile up and lean against a single number the way a tired head leans against a pillow. The arrow lands. The paradox dissolves, not with an argument, but with a sum. Then 2 men built the same machine twice. Newton, sent home from university by the plague, sat in a quiet farmhouse and watched quantities flow like water. Leibniz, in his study, drew the long, soft letter for summing and the small letter for difference, symbols so well shaped that we still write with them. Between them, the machine had 2 great gears. The derivative catches change at a single instant, the speed of now, the slope of a curve at one point. The integral gathers change back into a whole, adding countless slivers into an area, a distance, a total. And the fundamental theorem is the bridge between the gears. Cutting apart and gathering up are the same journey walked in opposite directions. For a long while, ghosts lived inside the machine. Quantities smaller than everything, yet somehow more than nothing. Amounts treated as zero in one line and not zero in the next. The critics were right to be uneasy, so mathematicians made a promise, the epsilon and delta promise. Tell me how close you demand to be, and I will tell you how near to come, and your demand will always be met. It sounds like a small courtesy. It was the foundation. The ghosts were laid to rest, and the whole cathedral finally stood on stone. After that, the one idea only grew bolder. Series add forever and still arrive. Infinite lists of terms folding themselves into waves and gentle exponential curves. Differential equations write the rules of change, and from those rules come the arcs of planets, the slow cooling of a cup of tea, the swirl of a thunderstorm. Born in a plague year now, steers satellites through the dark, traces the beating of hearts, and teaches machines to learn from their own mistakes. A young man hid from sickness in a farmhouse, and what he wrote there quietly lives on in the phone resting beside your bed. And beneath all of it, one move, repeated with more and more courage. Get closer, then closer than that, then closer still, past any distance anyone can name, and trust where the closeness is heading. That is calculus. It was never a wall of symbols. It is a way of sneaking up on the truth, so gently that the truth never startles and simply lets itself be seen. And that is the whole walk. If you are still awake, you do not need to be. There is nothing left to hold on to, and nothing you were supposed to remember. Wherever you faded tonight, at the triangles, or the arrow, or the quiet farmhouse, that was the right place to fade. The ideas do not mind. You were never meant to carry them all. You were only meant to let them pass through you, like slow water. They keep unfolding on their own, quietly, in the dark, the way a garden keeps growing after you have gone inside. The whole path will still be here tomorrow night. Every chapter waits for you without impatience. Tomorrow the triangles will still be leaning into their curve, and the arrow will still be landing, softly, forever. You can begin again anywhere, and drift away again anywhere, and none of it is ever lost. So let everything go soft now. Let the tangent line rest against its curve like a hand laid gently on a shoulder. Let the areas fill in slowly beneath their curves, the way breath fills you and leaves you and fills you again. The limits have all arrived. The sums have all settled. Every sequence has found the number it was leaning toward. Your thoughts can do the same. Let them drift closer and closer to nothing in particular. There is no test in the morning. There is nothing left to solve. There is only the slow arithmetic of breathing, in and out, a little slower each time. The infinite is tamed. The arrow has landed. The candle in the farmhouse is out. You can sleep now. Close your eyes. Get closer, Rhett.